In the last few decades, scientists and engineers began to imagine structures so huge that they would make any city on Earth look like a grain of sand. These ideas, which once existed only in fiction books, are now being studied for real by very smart people all around the world. What seemed impossible is getting closer and closer to becoming real. We're talking about 25 giant structures in space that could completely change the future of humanity. Some could capture all the energy from a star, others could be entire cities floating in the dark emptiness of the universe. This made scientists ask something incredible. Will we one day build things bigger than entire planets? Get ready to fall asleep while listening to this video and let your mind travel through these enormous possibilities. Subscribe to the channel, leave your like and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. Imagine you wanted to build the biggest thing possible. What would it be? Today, we are not talking about skyscrapers or even artificial continents. We are talking about re-engineering the very layout of a solar system, starting with the ultimate power plant, a concept that has become shorthand for an unfathomably advanced civilization. The idea is simple in principle but staggering in scale. Capture every single photon of light a star emits. This is the core of what we call a Dyson sphere. It is not usually imagined as a solid continuous ball, though that iconic image is what pops into most people's minds. That version, a rigid shell completely enclosing a star like a cosmic eggshell, is what Freeman Dyson, the physicist who popularized the concept, would likely call a Dyson shell. It's a beautiful thought experiment, but it is also a mechanical nightmare. The forces involved, the stress from the star's gravity, the need for impossible materials, the thermal management, it all makes a single solid shell profoundly unrealistic. So, let us talk about what a real Dyson sphere would probably look like, how we might actually build it, why we are looking for signs of them in the galaxy, and what building one would truly mean for a species. The more plausible configuration is a Dyson swarm. Think of it not as a shell, but as a dense, thick cloud of individual units orbiting the star. Each unit could be a power collection satellite, a habitat, a factory, or a combination thereof. These are often called Dyson satellites or statites if they use solar sails to hold position. The beauty of the swarm is that you can start small. A civilization does not need to build a full sphere all at once. They could begin with a few solar power stations in orbit around their home planet. Then they build more and more. Over centuries or millennia, they gradually increase the density of these constructs in space around their star, blocking out more and more of its light from an external view. Each satellite converts stellar energy into something useful: electricity for computation, beamed power for habitats, or direct thermal energy for industrial processes. The swarm is modular, redundant, and can be built with materials that actually exist or could be engineered. It is the slow, steady, and intelligent path to total stellar dominance. So where do you get the material to build billions or trillions of these satellites? You have to look around your solar system. The amount of matter required is astronomical, literally. A basic Dyson swarm capable of capturing a significant fraction of a star's output would require the dismantling of not just one planet, but likely several. This process is known as planetary mining or astroengineering. The most likely first candidate would be a gas giant's moons, or the rocky planets in the inner system without life, or the asteroid belt. Imagine fleets of autonomous machines, von Neumann probes perhaps, landing on Mercury. They would not dig mines. They would systematically tear the planet apart layer by layer, feeding its mass into space-based factories that turn raw rock and metal into solar panels, support structures and habitation modules. This is not construction as we know it. It is planetary recycling on a grand scale. It is the ultimate act of a civilization declaring that planets are not permanent homes, but raw material depots. The entire economic and industrial output of a species would be redirected towards this single, multi-generational project of restructuring their celestial neighbourhood. The energy output is almost impossible to comprehend. Our Sun, a fairly average star, emits about 386 septillion watts of power. That is 386 followed by 24 zeros. Currently, all of human civilization operates on a tiny, infinitesimal fraction of that. Even capturing 1% of a star's output would provide millions of times more energy than we use today. This level of energy mastery is what the Kardashev scale attempts to categorize. A Type 1 civilization can use all the energy available on its home planet. We are not quite there yet. A Type 2 civilization, which is what a species with a Dyson sphere would be, has harnessed the total energy output of its star. This is not just about having more electricity for lights, it is about having the power to do things we can only dream of. It could power interstellar propulsion for massive ships, fuel unimaginably complex supercomputers the size of planets, or sustain billions of habitats each hosting millions of beings. Energy at that point ceases to be a concern. It is abundant, like air or sunlight on Earth. This abundance fundamentally changes what is possible, shifting the limits from energy availability to material resources and pure imagination. How would we ever detect such a thing if another civilization had built one? This is where Dyson's original paper was so insightful. He was not an engineer dreaming of construction. He was a physicist thinking about detection. A star surrounded by a dense swarm of energy-collecting structures would look very strange to us. The visible light from the star would be largely blocked, absorbed by the satellites. But energy cannot be created or destroyed, only changed. That absorbed starlight does not vanish. The satellites, whether they are habitats or power stations, have to radiate the energy away as waste heat to avoid melting. This waste heat is emitted as infrared radiation. So, to an outside observer, a star with a Dyson swarm would appear as a dim or even dark object in the visible spectrum, but it would glow brightly in the mid-infrared. Astronomers have actually looked for these signatures. They have scanned the sky for objects that are exceptionally bright in infrared, without a corresponding visible light source. A few candidates have popped up over the years, stars with unusual dimming patterns and infrared excess, but so far everyone has had a plausible natural explanation, like a cloud of dust or a swarm of comets. The search continues, and it remains one of the most concrete methods in the SETI toolbox, not looking for radio signals, but looking for the colossal engineering projects of other beings. Let us think about the living reality inside a Dyson swarm. It is not a single, giant room. It is a vast three-dimensional archipelago in space. The individual habitats could be O'Neill cylinders, Bernal spheres, or simpler enclosed structures. They would orbit the star at various distances, each likely positioned in the Goldilocks zone, where temperatures are right for their purpose. Some might be agricultural rings, endless fields under artificial suns. Others might be dense, urbanized worlds. Between them, a constant traffic of ships would move, transporting people, goods, and information. The night sky inside a habitat in a dense swarm would be fascinating. You would not see many stars, because the swarm itself would block them out. Instead, the sky might be dotted with the illuminated surfaces of other nearby habitats, glowing like strange geometric constellations. The central sun might be visible only as a diffuse softened glow, its direct light carefully managed and filtered by the swarm's infrastructure. Life would be entirely artificial, but on such a scale that it could feel as natural as life on Earth, with parks, weather cycles and ecosystems all meticulously maintained. What does it take for a species to embark on such a project? The prerequisites are immense. First, you need unity, or at least a dominant, stable governing force that can pursue a project lasting centuries. It requires technology for fully automated, self-replicating industry in space. It requires a mastery of material science we do not yet possess. But more than anything, it requires a fundamental shift in mindset. A civilization building a Dyson sphere has effectively decided that planets are obsolete. They have outgrown their planetary cradle. Their future is in space, in environments they control down to the last molecule. They are no longer subjects of their star's whims. They are its stewards and beneficiaries. The construction of a Dyson swarm is the declaration of a transition from a planetary species to a stellar one. It is the moment a civilization looks at its sun and says, "This is our engine, and we will plug into it." It represents a move from scarcity to such profound abundance that the very nature of society and economy and purpose would be rewritten. The challenges are beyond our current grasp, but the principle is clear. If you want to grow without limits, you must learn to build on the scale of your star. And that journey begins not with a solid shell, but with the first autonomous factory that lands on an asteroid and starts building copies of itself, initiating the long, slow process of weaving a net around a sun. So, if a Dyson swarm is about harnessing the energy of a star, the very next question becomes a practical one. Where is everyone going to live? You have all this power. but you're still dealing with the limitations of planets, with their deep gravity wells and fixed, often fragile environments. The logical next step, the first major habitat after mastering basic space stations, is not a planet at all, but a ring. Imagine a wheel in space, so vast that its curve appears flat, rotating to create gravity along its inner rim. This is the concept of an orbital ring habitat, a structure designed not for energy capture, but purely for providing expansive, controllable living space for millions. It is the foundational idea behind turning space itself into a place for civilization, not just a void to cross. Think of it as the first real city we build that has no connection to a planetary surface, a completely artificial world where every mountain, every river, and every breath of air is by design. The principle is straightforward and relies on a classic physics demonstration: centrifugal force. Spin something fast enough and things get pushed outward. In a rotating ring, the outward direction is toward the outer rim. So, if you build your living floor on the inside of that outer rim, the spin pushes you against it, simulating gravity. The ring rotates as a whole, a giant rigid hoop. The speed of rotation is carefully calculated. Too slow, and the simulated gravity is weak, like on the moon. Too fast, and you might induce dizziness or Coriolis effects, where moving your head feels strange. The sweet spot for a large ring, one with a diameter of several kilometers or more, is a rotation that creates a comfortable one-Earth gravity along its inner circumference. This creates a truly bizarre and wonderful landscape. The ground you stand on curves upward in both directions, forming a valley that arcs over your head. If the ring is large enough, say a mile or two in diameter, this curve is gentle enough that the horizon rises before you, creating the illusion of a long, shallow valley. In a truly massive ring, dozens of miles across, the curve might be so slight that it feels nearly flat, with the opposite side of the ring hidden by the atmosphere and distance, seeming like distant arching mountains. What would you see when you look up? Instead of a sky leading to space, you would see the rest of the ring's interior stretching across the void. The ceiling would be land, cities and lakes hanging overhead, illuminated by an artificial sun running down the central axis of the structure. This central axis is a crucial part of the design. It is a non-rotating spine, a long, thin cylinder running right through the middle of the ring. This is where the zero-gravity docks, control centres, and external observation decks would be located. From this central hub, you could take an elevator or a shuttle down cables to the rotating ring below, gradually feeling the pull of artificial gravity increase as you descend. The central axis also houses the primary lighting system, a long tubular lamp or a series of mirrors that direct sunlight in from outside, creating a bright linear sun that cycles on and off to simulate day and night. This gives the entire interior a consistent, controllable light source, independent of any external orbital cycles. The interior of the ring's rim is where life happens. The surface area, while not planetary in scale, is immense. A single orbital ring with a diameter of 1 kilometre provides several square kilometres of living space. One with a diameter of 10 kilometres provides hundreds. You could design this interior landscape like a giant enclosed terrarium. One section could be urban, dense, vertical cities with efficient transportation systems. Another could be agricultural, with vast fields and orchards under the artificial sun, growing food for the entire population. There could be recreational lakes, rivers engineered to flow in a loop, and forested parks. The weather would be fully managed: precipitation, temperature, humidity, all controlled by the habitat's environmental systems to be perpetually ideal, or programmed to have gentle seasons for variety. The atmosphere is contained by the rigid hull of the ring itself, which is strong enough to hold in the air pressure and protect against cosmic radiation and micrometeoroids. It is a completely closed, self-sustaining ecological system, a biosphere in a can, but a can shaped like a colossal hoop. Why build this instead of just colonising Mars or the Moon? Control and efficiency. On a planet, you're fighting the existing environment. Gravity is what it is. The atmospheric pressure is what it is or isn't. The day-night cycle is fixed. The radiation exposure is a constant problem. An orbital ring habitat lets you design every single parameter from scratch. You set the gravity to 1G, perfect for human health long term. You set the atmospheric composition to optimal levels. You have no harmful solar radiation or cosmic rays because the hull shields it all. You decide the length of the day. Furthermore, Its location in space offers strategic advantages. It can be placed in a stable orbit around Earth, or around the Moon, or at a Lagrange point, those gravitational sweet spots where things tend to stay put. This makes it an ideal hub, a port of call for travel within the solar system. Ships coming from Mars or the asteroid belts can dock at the zero-G hub without having to fight a planet's gravity well, exchange cargo and passengers, and be on their way. It becomes a centre of trade, culture and governance, unburdened by any planetary history or territorial disputes. The construction of such a ring is the first true test of large-scale in-space manufacturing. We are not talking about assembling modules launched from Earth. That would be impossibly expensive. We're talking about building the ring from materials sourced from the Moon, from asteroids. The process would likely start with the central axis, a non-rotating framework. Then, using material launched via mass drivers from the lunar surface, we would begin constructing the ring itself in segments. These segments, likely hollow truss sections, would be attached to the axis and gradually spun up. As the ring grows, the spin is carefully adjusted to maintain structural integrity. The process would be slow, taking decades, and would require a permanent workforce living in construction shack modules. The final step would be the most delicate: installing the interior landscape, shipping in soil, planting ecosystems, filling water reservoirs, building cities, all inside a rotating structure. It is a project that would define generations, but the result is a permanent, scalable piece of real estate in space. Once you have the first one, you know how to build a second and a third. You can link them together, creating clusters of rings, a necklace of worlds around a planet or star. Life inside would be different, but quickly normal. The psychological adjustment to a curved world with a sky of land overhead would be significant at first, but humans adapt. Transportation within the ring would likely be a combination of trains running along the rim and personal vehicles on roads. To travel to the other side, you would not go around. You would take an elevator up to the zero-G axis, float across to a corresponding elevator shaft, and descend down the other side. Sports would be fascinating. Playing ball games could get complicated with the Coriolis effect, but new sports would emerge. The economy would be based on high-tech manufacturing, information services, and perhaps tourism for those wanting to experience this unique way of life. It would be a society born of engineering, likely placing high value on sustainability, system maintenance, and collective responsibility, because a failure in the life support systems is a failure for everyone. There are no open windows, no escape to the countryside. The entire environment is technological. The orbital ring is more than a habitat, it is a statement. It says that a species is ready to create its own worlds, tailored to its needs rather than adapt to the ones it found. It is the intermediate step between the planetary cradle and the stellar civilization of a Dyson swarm. Before you can dismantle planets for megastructures, you need to know how to build robust, permanent habitats in space that can house the workforce and the culture that will undertake that project. The ring is that practice run. It is where we learn to manage closed ecologies on a scale of millions of people. It is where we perfect artificial gravity. It is where we become truly spacefaring, not just space visiting. The International Space Station is a cramped laboratory. An orbital ring is a homeland. It represents the point where humanity, or any civilization, decides that its future growth and expansion will happen in the vast volume of space, using the materials and energy there, and that the first and most important thing to build is a place to call home, a place that you built with your own hands, floating in the silent dark, a beacon of light, life, and incredible ambition. This vision transforms our relationship with the cosmos from one of visitation and exploration to one of residence and construction, setting the stage for every larger and more complex structures that might follow, each pushing the boundaries of what a civilization can achieve when it thinks in terms of solar systems rather than continents. Now, if an orbital ring feels like a town or a small country in space, what comes next is the vision for a true city, or even a whole nation floating independently. This is where we move beyond a single ring and start thinking in terms of cylinders. The concept is most famously tied to the physicist Gerard K. O'Neill, who in the 1970s worked out the practical details for massive space habitats that could house millions with a quality of life arguably better than Earth's. These O'Neill cylinders are not just bigger stations, they're engineered landscapes, complete with their own skies, weather cycles, and a sense of openness that, a ring with its overhead land cannot provide. They represent perhaps the most detailed and compelling blueprint we have for permanent, comfortable life away from our home planet. The core idea is a pair of giant cylinders, each one rotating to create gravity on its inner surface, and they spin in opposite directions to cancel out gyroscopic effects that would make them hard to steer. Each cylinder is colossal, measuring up to 20 miles long and 5 miles in diameter. That is a living area of over 300 square miles per cylinder, and you have 2 of them. That is a lot of room to build a new world. The interior design is where the O'Neill cylinder shines. The inside of the cylinder is not a single continuous landscape. Instead, it is divided lengthwise into 6 equal strips, running the entire 20-mile length of the cylinder. Think of 3 window strips and 3 land strips alternating like the segments of an orange. The 3 window strips are massive transparent panels made of a strong material like fused silica. They are not open to space, they are structural, holding in the air. Opposite each window strip on the other side of the cylinder's interior is a corresponding land strip. This is the ground you live on. So, you have land, then a window, then land, then a window, and so on, all the way around. Now, here is the brilliant part. The cylinder is not pointed at the sun. Its long axis is perpendicular to the sun's rays. Huge stationary mirrors are positioned outside each cylinder. These mirrors reflect sunlight in through the windows, flooding the interior with natural light. By tilting these mirrors, you can simulate a day and night cycle. You can even create seasons by varying the amount of light let in over a yearly cycle. The light comes in at an angle, illuminating the opposite land strip. So when it's day in your section, the sun appears to rise over the window strip across from you, travel across the sky, which is the vast open interior space, and set behind the window strip on your other side. This creates an environment that feels astonishingly Earth-like, but with surreal differences. The ground curves up and away from you, but because the cylinder is so wide, the curvature is gentle. The land strips are wide enough to have rivers, lakes, small mountains, forests, and cities. Looking up, you do not see land hanging overhead like in a ring. Instead, you look across a vast open space to the other side of the cylinder, 3 land strips and 3 window strips away. That other side is miles away. You would see clouds possibly, and the details of the distant landscape would be hazy with atmosphere, just like a far-off horizon on Earth. The sky is not a dome, it is a long straight tube of space stretching to the ends of the cylinder where it is capped. The sense of openness is profound, a psychological game-changer for long-term space habitation. You would have real weather. Clouds would form from evaporated water, rain would fall, and gentle winds would circulate as different parts of the interior heated up slightly differently from the simulated sunlight. It is a fully managed but dynamic ecosystem. Living there would involve a mix of the familiar and the novel. Towns and cities would be built on the land strips. Transportation along the length of the cylinder could be by train or maglev. To go around the other side, you would not need to go up to zero gravity. You could simply take a bridge or a tunnel through the end cap, or even a short-flight aircraft across the interior space. Agriculture would happen in dedicated sectors, possibly in specialised smaller cylinders or in vast greenhouses on the land strips. The day-night cycle, controlled by the external mirrors, would be perfectly regular, perhaps with longer summer days and shorter winter ones for variety. The climate would be idyllic by design. No hurricanes, no droughts, no extreme heat waves. The temperature, humidity and air composition are all maintained by the habitat's life support systems, which recycle everything with near-perfect efficiency. Water is used, cleaned and reused. Waste is processed into fertilizer. It is the ultimate expression of a sustainable circular economy, because there is no outside environment to pollute or draw unlimited resources from. Every molecule counts. The construction of such a thing is of course a monumental undertaking. O'Neill and his students realistically propose building them at the Lagrange points, specifically L4 or L5 in the Earth-Moon system. These are gravitational balancing points where an object can stay in a stable position relative to both bodies with minimal effort. This is a safe location, far from Earth's orbital debris and with easy access to lunar materials. That is the second key part of the vision, using non-terrestrial resources. The cylinders would be built almost entirely from lunar or asteroid material. The Moon has abundant aluminum, titanium and silicon for glass. Using a mass driver, an electromagnetic catapult on the moon's surface, you could launch mined material into space with no rocket fuel or cost. Factories at the construction site would process this raw material into beams, plates and cables. The construction sequence would likely start with the zero-gravity hubs at each end, then the central spine, and then the cylindrical hull would be built outward like a slow, expanding barrel. Installing the window panels would be a tense operation, as they're critical pressure hull components. Finally, the immense task of terraforming the interior would begin, bringing in water from asteroids, manufacturing soil, introducing plants and microorganisms to create a balanced biosphere. So why go through all this trouble? The O'Neill cylinder is a solution to several fundamental problems. First, it offers a permanent escape from planetary resource limits and environmental risks. Second, it provides genuine expansion room for a growing civilization without the ethical and ecological complications of terraforming another planet. Third, it is a testbed for total environmental control, skills necessary for any long-term future in space. But perhaps most importantly, it offers a choice. On Earth, we have one gravity, 1 day length, 1 atmospheric pressure. In an O'Neill cylinder, you could in theory adjust the spin rate for different gravities. You could have cylinders with moon gravity for retirees or for industrial processors that benefit from it. You could have cylinders with a 20-hour day cycle if that proved better for human health. You are designing the world to suit its inhabitants, not the other way around. This represents a shift from being creatures of a planet to being architects of worlds. The psychological and social implications are deep. A society born in such a place would likely have a very different relationship with nature, seeing it as a beautiful, essential, but entirely engineered system to be maintained with precision. They would be intensely aware of their dependence on technology, fostering a culture of rigorous education and system responsibility. The challenges are immense, from the material science needed for the windows and structure, to the ecological balancing act of a closed biosphere of that scale, to the sheer economic and organisational effort. Yet, the O'Neill cylinder remains the gold standard for serious concepts of large-scale space colonisation because it addresses the human need for space, for a naturalistic environment, and for autonomy in a tangible way. It is not a distant Dyson swarm or a fanciful ring world. It is a logical, if gigantic, extension of the space station and orbital ring concepts. Building the first one would be the single greatest engineering project in human history, but it would also be the creation of the first truly new land for humanity in millennia, a land not stolen from anyone, not fought over, but built from the raw stuff of the cosmos. It is a vision that says our future is not about finding another Earth, but about learning to build better ones ourselves, and in doing so, we take control of our destiny in a way that staying on any planet, no matter how nice, never could. This step transforms humanity from a species that lives on a world to one that builds worlds, setting the stage for an era where the solar system itself becomes the substrate for civilization, with countless such habitats eventually dotting the space around our sun, each a unique experiment in living, culture and environment. The cylinder is more than a habitat. It is a declaration of independence from the planetary chance that birthed us, a conscious step into a designed future. Building those cylinders, those rings, those massive habitats, all sounds incredible until you hit the single biggest practical problem. How do you get millions of tons of material from the surface of the Earth into space without going bankrupt? Rockets are spectacularly expensive, inefficient and limited. They are the equivalent of building a transcontinental railway where every single piece of track is launched by a catapult and then thrown away. For true space industrialization, we need a railway itself, a permanent, reusable and cheap infrastructure. That is the promise of the space elevator, a concept so simple in idea and so monstrously complex in execution that it could single-handedly unlock the solar system. Forget rockets, imagine a cable, a tether, stretching from the surface of the Earth all the way up to a point far beyond geostationary orbit, with elevators climbing up and down it, delivering cargo and people for a fraction of the cost. This is not just a better rocket, it is a fundamental shift in how we access space, turning it from a daring expedition into a routine commute. The basic principle relies on orbital mechanics and centrifugal force. Geostationary orbit is that special altitude, about 35,786 kilometers up, where a satellite orbits at exactly the same speed the Earth rotates, so it appears to hang motionless over one spot on the equator. Now imagine you attach a cable to that satellite and drop it down to Earth. At the same time, you extend a cable from the satellite outward, away from Earth, to an even higher altitude. This outer section is crucial. The entire system, the long cable, the counterweight at the far end, and Earth at the bottom, is spinning with the planet. The centrifugal force pulling the counterweight outward balances the gravitational force pulling the cable inward. The result is a tensioned structure, a taut line stretching from the ground into space. The elevator itself is a climber, a mechanical vehicle that grips this cable and uses electric power, likely from lasers or solar panels, to drive itself up and down. Up goes finished habitat modules, construction robots, and settlers. Down could come finished products from space factories or even solar power. The climber does not need to carry immense fuel, it just needs traction and power, making it incredibly efficient. The showstopper, the one thing that has kept this a science fiction for decades, is the cable material. It needs to be unbelievably strong and light. Steel would snap under its own weight long before reaching the necessary length. The required material strength is measured by something called the specific strength. For a space elevator from Earth, you need a material with a tensile strength far beyond anything we commonly use. For a long time, this seemed impossible. Then, carbon nanotubes entered the scene. These are microscopic tubes of carbon atoms arranged in a hexagonal pattern, and they have a theoretical specific strength that is orders of magnitude greater than steel. They are the only material we know of that might be up to the task. The challenge is we cannot yet make carbon nanotubes in mass quantities, and certainly not in the form of a flawless, macroscopic cable tens of thousands of kilometers long. A single defect, a weak spot, could cause a catastrophic failure. So, the first and greatest hurdle is material science. We need to learn to manufacture perfect nanoscale materials on an industrial scale. Some researchers think newer materials like graphene or boron nitride nanotubes might also be contenders. Until this material problem is solved, the Earth space elevator remains a dream. But let us assume we crack the material science. The construction begins. You would likely start by launching the initial seed cable, a thin thread of the super strong material on a traditional rocket to the geostationary altitude. This is the hardest rocket launch ever, because it has to deliver this spool correctly. From there, you would lower a cable down to a mobile ocean platform stationed on the equator, while simultaneously deploying the cable outward to a massive counterweight. This counterweight could be a captured asteroid, a spent rocket assembly, or a purpose-built station. Once the initial tether is anchored and tensioned, the real work begins. Robotic climbers would start going up and down this initial thin cable, adding more strands, weaving and reinforcing the tether, making it thicker and stronger with each trip. It is a bootstrap process, building itself stronger using the very access it provides. Over years, the thin thread becomes a ribbon, then a cable, then a truly robust structure capable of carrying heavy loads. The base station on Earth would be a massive offshore platform, like a floating oil rig, located in the calm equatorial Pacific. It needs to be mobile to maneuver and avoid storms, and it is here where the climbers would be loaded and launched. The advantages are so transformative it is hard to overstate them. Current rocket launches cost thousands of dollars per pound to get to low Earth orbit. A mature space elevator could drop that cost to tens of dollars per pound, maybe even less. It is the difference between shipping a package by courier jet and putting it on a container ship. This cost collapse changes everything. Suddenly, building an O'Neill cylinder is not a multi-trillion-dollar fantasy. It is a large but manageable infrastructure project. Solar power satellites become economically viable. Space tourism becomes commonplace. The elevator provides a constant, slow and steady throughput of mass. It is not fast. The climb might take days or a week, but it is relentless and cheap. You could send up the parts for an entire space station in a continuous stream, like building a skyscraper where bricks arrive on a conveyor belt instead of by truck. It democratizes space access, allowing universities, small companies and even individuals to send up experiments and equipment. It is the great enabler, the foundational infrastructure upon which every other megastructure concept relies if it wants to use Earth-sourced materials or personnel. Of course, the dangers and challenges are terrifying. A breaking cable would be one of the worst disasters imaginable. If it snapped near the anchor point, the entire thousands of kilometres long cable would whiplash into space, wrapping around the planet, potentially destroying satellites and creating a persistent debris field. If it snapped higher up, sections could deorbit and rain down along the equator. The system would need multiple redundant strands and constant health monitoring. Then there is the issue of orbital debris and micrometeoroids. A tiny piece of space junk travelling at orbital speeds could sever the cable. Active defence systems, like tracking and gentle laser nudges to move debris, would be mandatory. The climbers themselves would need to navigate through the Van Allen radiation belts, requiring shielding for any human passengers. Geopolitical tensions around the base station would be intense. Who controls the elevator controls the gateway to space, leading to a likely international consortium managing it. Weather, especially lightning, would be a constant threat at the lower atmosphere section. Perhaps the most pragmatic path forward is to start smaller. The Moon is a prime candidate for the first space elevator. Because the Moon's gravity is 1/6 of Earth's and it has no atmosphere, the required cable strength is within the reach of existing materials like Kevlar or Xylon. A lunar space elevator could be built with today's technology, anchored on the Moon's surface and extending out to a Lagrange point. This would facilitate the movement of mined lunar material into a stable location for processing and launching throughout the solar system, proving the technology and economics before we attempt the Herculean Earth version. An elevator on Mars is also more feasible than on Earth, so the development path is clear. Master Materials build a lunar elevator as a test bed and use that experience and the resources it provides to eventually tackle the grand challenge of an Earth elevator. In the end, the space elevator is the ultimate symbol of long-term thinking. It is not a vehicle for a single mission. It is a permanent piece of planetary infrastructure, like the internet or the electrical grid. Its construction would be a multi-generational commitment, a project spanning decades. But its completion would mark the moment humanity truly became a spacefaring species, not just visiting the cosmos in fragile shells, but establishing a permanent, affordable and heavy-lift connection to it. It is the bridge between the planet of our birth and the future we hope to build among the stars. All the other megastructures we dream of, the Dyson swarms, the orbital rings, the cylinder cities, they all depend on solving the launch problem first. The space elevator is that solution, the foundational keystone in the arch of a spacefaring civilization. It turns the energy of our planet's rotation into a slingshot to the stars, a silent, steady, and eternal ladder waiting for us to climb. So, a space elevator seems like a massive undertaking, a project that would define a century. But in the grand scheme of megastructures, it is merely the humble front door, the utility corridor. Once you have that cheap access to space, and you start thinking in terms of dismantling planets for building materials, your imagination can start to race towards constructs that make even an O'Neill cylinder look like a garden shed. This brings us to the ultimate expression of living space, the endpoint on the scale of artificial worlds, the ring world. Made famous by author Larry Niven, the ring world is not a sphere around a star, and it is not a cylinder. It is a literal band, a ribbon 1,000,000 miles wide, that forms a perfect circle around its sun at the distance Earth is from our sun. Think of it as a cosmic racetrack, with the star fixed at the centre like the hub of a wheel. The scale is so absurd, so incomprehensibly vast, that it pushes the concept of engineering into the realm of pure mythology. It is less a blueprint and more a thought experiment about the outermost limits of ambition. Let us try to grasp the dimensions, because they are everything. The ring has a radius of 1 astronomical unit, 93 million miles. That means its circumference is over 580 million miles. It is 1,000,000 miles wide from its inner edge to its outer edge. To put that in perspective, if you took the ring world and laid it out flat, its surface area is equivalent to about 3 million Earths. 3 million planets worth of land all in one continuous artificial landscape. The sun sits permanently at the centre of the circle, illuminating the inner surface of the ring. There is no day and night cycle from the sun itself. It is always high noon directly overhead at the ring's central line, so how do you get night? In Niven's design, a second ring of shadow squares orbits independently between the ring and the sun. These are enormous, opaque panels that move in a precise dance to cast moving shadows across the landscape, creating a day-night cycle and even seasons as their patterns change. The ring rotates to provide artificial gravity. The spin is not for creating Earth-like gravity through centrifugal force. At that radius, the rotational speed needed for 1G is far too high. Instead, the ring spins at a speed that provides a small outward force, but the primary source of gravity is actually the mass of the ring itself. Its sheer planetary mass generates its own gravitational field, pulling down toward the inner surface. Now imagine standing on that surface. You're on a plane that is flat as far as the eye can see, but with a crucial difference. Look to your left and right, and the land stretches to a horizon so distant it is blurred by atmospheric haze. But look up, and instead of a sky that arcs overhead, you see a band of land curving up from both horizons, arching all the way across the heavens to meet on the opposite side of the sun. The landscape is overhead, thousands of miles away, illuminated by the same central sun. It would be a dizzying, overwhelming sight, a constant reminder that you are inside a made thing of impossible size. The sun itself is a small, brilliant disk fixed at the centre of this arch of land. The atmosphere is held in by walls on each edge of the ribbon. These are not small walls, they're 1,000 miles high, mountains so tall they scrape the vacuum of space, containing the air over the million-mile width. On these walls, you could have weather patterns, snow caps, and entire civilizations living on their slopes. The engineering and material challenges are so profound they break known physics. First, you need the material. The ring world requires far more mass than exists in all the planets of a typical solar system combined. You would have to disassemble every single planet, every asteroid, every comet, and still probably need to harvest matter from other stars. Second, you need a material with unimaginable tensile strength. No known or theorized substance, not even carbon nanotubes, could withstand the stresses involved. The ring is under immense tension, as every part of it is trying to drift toward the sun. The spin is not enough to hold it perfectly stable. It requires an impossible material called skrith in the novels, a substance that is transparent to neutrinos and has the strength of the strong nuclear force. Third, there is the stability problem. A ring world is dynamically unstable. If it gets slightly off-centre, the gravitational pull from the star will grow stronger on the closer side, pulling it further off-centre until it crashes into the sun. You would need an active stabilisation system, like massive thrusters on the rim, constantly firing to keep it perfectly centred, a maintenance nightmare for eternity. Then there are the practicalities of living there. With a surface area of 3 million Earths, the population could be quintillions of beings. The ecological management is beyond comprehension. You would have to engineer entire continental-scale biomes, mountain ranges and oceans. Weather systems would be planetary in scale, but confined to a strip. The sheer logistics of governance, transportation and communication across hundreds of millions of miles of continuous territory are insoluble by any system we can imagine. It is the ultimate monument to central planning gone cosmically mad. Furthermore, with no day-night cycle from the primary sun, the shadow squares are a single point of catastrophic failure. If their orbit decays or they collide, entire swaths of the ring could be plunged into permanent day or night, causing ecological collapse. So why even discuss it if it is impossible? Because the ring world serves a crucial purpose as a thought experiment. It forces us to confront the limits of scale. It asks the question, what is the absolute most living space you could possibly create around a star? It helps define the boundary between plausible astroengineering and godlike creation. It also highlights the appeal of more modular swarm-based approaches like Dyson swarms, or even networks of O'Neill cylinders. Those are redundant, scalable and repairable. The ring world is a single point of failure monolith. In comparing it to realistic megastructures, we appreciate the wisdom of building many small things instead of one inconceivably large thing. The ring world is the ultimate big dumb object, a trope in science fiction that inspires awe precisely because of its impracticality. Could a civilization ever build something even remotely like it? Perhaps, but not as a single rigid band. A more plausible, though still vastly challenging concept is the Bishop Ring, a much smaller rotating habitat only a few hundred miles wide and with a radius of maybe 1,000 miles. But the classic Niven Ring world, it stands as a symbol. It represents a civilization that has reached such a level of power that it views solar systems as raw clay to be sculpted. It is a Kardashev Type 3 civilization's playground, a project undertaken not out of necessity, but out of a sheer, boundless will to create and to own a piece of the cosmos yet in the most literal way possible. It is the architectural equivalent of a shout into the galaxy, a declaration that we were here and we reshaped the very fundamentals of our star system. While we will almost certainly never build one, thinking about it stretches our minds. It makes the O'Neill cylinder seem reasonable, the Dyson swarm seem prudent. It is the extreme end of the spectrum, a reminder that once you start building with planets as your bricks, there is no obvious upper limit to ambition, only the hard limits of physics and material science that, for now, firmly tell us this far and no further. The dream of the Ringworld, therefore, is not a practical guide, but a celestial yardstick against which we measure all other dreams of building in space. While the Ringworld is a fantastic monument to ultimate ambition, our immediate needs here on Earth are far more pressing and practical. We are facing a tangible energy and climate crisis, and we need solutions that could work within decade, not millennia. This brings us down from the dizzying heights of stellar megastructures to a concept that is still huge, but fundamentally achievable with technology we either have or can see on the horizon, the orbital solar farm. This is not a Dyson swarm capturing all of a star's output. It is a more modest, targeted megastructure designed to solve a single critical problem, providing clean, abundant and constant power to our home planet. Imagine vast arrays of solar panels, miles across, floating in a high Earth orbit, silently collecting sunlight 24 hours a day, 365 days a year, and beaming that energy safely down to the surface. It sounds like science fiction, but it is arguably the most sensible and impactful first giant step into space-based industry. The core advantage is simple: location. Solar power on Earth is plagued by intermittency. Night stops it, clouds block it, seasonal changes reduce it. In geostationary orbit 22,000 miles above the equator, a solar array is in constant unfiltered sunlight. There is no atmosphere to scatter or absorb the light, so the solar energy is about 30% more intense. A satellite in this orbit stays fixed over the same spot on Earth, meaning it can transmit power continuously to a single receiving station. This solves the baseload problem of renewable energy at a stroke. You're not storing energy for the night in massive battery banks. You're simply collecting it where the sun always shines and sending it where it is needed, day or night, rain or shine. The scale of such a farm would be enormous, perhaps several square miles of photovoltaic panels or mirrors, but it is a construction project, not a physics-defying miracle. The magic and the major technological hurdle is in the transmission. You cannot run a wire 22,000 miles long, so you convert the collected electricity into something that can travel through space and the atmosphere, either microwaves or lasers. The most developed concept uses microwaves. The orbiting farm would have a massive microwave transmitter, a phased array that can precisely aim a low-intensity beam. On the ground, in a remote secure area, you would have a receiving antenna called a rectenna, which is a grid of simple wire dipoles and diodes that convert the microwave energy back into direct current electricity. The beam is not a dangerous, blazing laser cutter. It is a diffuse microwave beam with an intensity at the centre, roughly equivalent to the sun's warmth. Birds could fly through it safely, and the area around the rectenna could still be used for farming or other purposes. The system is designed to be inherently safe. If the aiming were ever lost, the beam would defocus and dissipate harmlessly in the atmosphere. Why would this be better than just covering deserts with solar panels? Several reasons. First, land use. A rectenna on the ground might be large, but the land underneath it is still usable. A massive solar farm in the desert, while helpful, still occupies that land exclusively and requires long transmission lines to population centres. An orbital farm has a tiny physical footprint on Earth. Second, constancy and predictability. The energy output is perfectly predictable, a flat line of maximum generation at all times, making the electrical grid far easier to manage. Third, global reach. A network of such satellites could beam power to virtually any point on Earth, providing energy to remote islands, disaster zones, or developing regions without building massive ground infrastructure. It is the ultimate in energy distribution flexibility. The challenges, of course, are immense. The first is cost of launch, which is why the space elevator discussion is so relevant. Launching the thousands of tons of material for a single operational farm using current rockets would be prohibitively expensive. This project only becomes viable with dramatically cheaper access to space, through reusable heavy-lift rockets, space elevators, or lunar resource utilization. The second challenge is in-space construction and assembly. We are talking about structures kilometers across that cannot be launched folded up like origami. They would need to be assembled by robots or astronauts in orbit, a technology we are only beginning to develop with projects like the International Space Station. We would need automated fabrication and assembly on an industrial scale. Third, there is the efficiency of the power transmission. We need to minimize losses at each step: photovoltaic conversion in space, electricity to microwaves, beam transmission through the atmosphere, and microwave to electricity on the ground. Each stage has inefficiencies, and the total system efficiency will determine the economic payoff. Current lab models suggest a path to viability, but it needs engineering at scale. Then there are environmental and social concerns. What are the long-term effects of a gentle microwave beam passing through the atmosphere? Extensive studies suggest it would be negligible, but public perception is a huge hurdle. The phrase beam of energy from space conjures fears of weaponization or accidental frying. Clear, transparent international safety standards would be essential. There is also the issue of space debris. A giant, fragile solar array is a big target. A collision with even a small piece of debris could be catastrophic. Active debris removal and careful traffic management in geostationary orbit would become critical national infrastructure priorities. Finally, there is the geopolitical dimension. Whoever owns and operates such a power source holds significant strategic influence. It would likely require an international consortium, similar to the International Space Station, to fund, build and govern such a system, ensuring its benefits are shared and its operation is secure from conflict. The path forward is likely incremental. We will not build a full-scale farm first. We will start with small, experimental prototypes. Researchers are already testing the components. There have been demonstrations of wireless power transmission over short distances, and companies as well as space agencies have designed small test satellites. The next step is a modest-sized demonstrator in low Earth orbit that beams a few kilowatts of power to a military base or remote community, proving the safety and feasibility. After that, a larger pilot plant in geostationary orbit, perhaps providing power for a small city. Each step lowers the technological risk, improves the efficiency, and builds the political and economic case for the full-scale version. This iterative proof-of-concept approach is how we turn a grand vision into a practical engineering program. In the grand narrative of megastructures, orbital solar farms are the bridge. They are the project that justifies developing the cheap space access and in-space construction techniques needed for the O'Neill cylinders and the Dyson swarms. They provide a direct, profitable, and earth-saving reason to learn how to build big in space. They transform space from a destination for exploration into a location for industry, an industrial park in the sky whose product is pure energy for the world below. Success here would create the economic engine, the technical workforce, and the political framework for everything that comes after. It is the megastructure that answers the question, why should we spend money up there? With a clear, compelling answer, to secure a clean, prosperous, and unlimited energy future down here. It turns the dream of space-based solar power from a perennial technology of the future into an actionable blueprint for the next century of human development, proving that the first and most important megastructure we build might not be for living in, but for powering the home we already have. This practical application serves as a crucial stepping stone, demonstrating that space industrialization has immediate, tangible benefits, thereby building the necessary momentum, capital, and public support to venture further into the cosmos for more ambitious projects. The orbital solar farm is not just a power station, it is the training wheels for a spacefaring civilization. The orbital solar farm gives us a powerful reason to be in space, but once we are there building those immense power arrays, the next logical question is about where the people who build and maintain them will live, and eventually where a larger population might reside permanently. We have talked about cylinders and rings, but there is another elegant shape in the cosmic architect's toolkit, the sphere. Spherical space habitats, like the Bernal sphere and the more modern Mackendry cylinder concept, offer a different set of advantages and challenges compared to their cylindrical cousins. They represent the pursuit of the most efficient and perhaps psychologically comfortable form for a completely enclosed, self-contained world. Think of it as the ultimate bubble, but one where you live on the inside surface with the entire world curving gently around you. The fundamental appeal of a sphere is geometric efficiency. For a given volume of interior space, a sphere has the smallest possible surface area. In space habitat terms, this is a big deal. The hull is what keeps the air in and the radiation out. Minimizing surface area means you need less hull material to enclose the same amount of living space, which reduces mass, cost, and construction complexity. It also means there is less area to shield from cosmic rays and micrometeoroids. So, from a pure engineering standpoint, a sphere is the most material-efficient pressure vessel you can build. The challenge, of course, is creating artificial gravity. You cannot spin a sphere like a top to create gravity everywhere inside. If you spin a sphere, you only get useful centrifugal force around its equator. The further you go from the equator toward the poles, the weaker the simulated gravity becomes, until at the poles themselves you are effectively in zero gravity. This is where the classic Bernal sphere design comes in. Proposed by scientist John Desmond Bernal decades before O'Neill's work, the concept is a spherical habitat where people live on the inner surface of a band around the sphere's equator. The sphere rotates, creating Earth-like gravity in this equatorial tropics region. The areas closer to the poles would be low-gravity zones, suitable for storage, industry or recreational activities like flying sports. The central core of the sphere, along the axis of rotation, would be a zero-gravity area, perfect for docking ports, observatories and microgravity research facilities. In this model, the sphere is not entirely filled with a landscape. Instead, the habitable area is a ring-like band inside a larger spherical shell. Lighting could be provided by a combination of mirrors on the outside directing sunlight in through windows near the poles, or by an artificial sun line running along the rotational axis. A more recent and ambitious concept is the McKendree cylinder, named after NASA engineer Thomas McKendree, though it is important to note this is actually a sphere-based design. His idea leverages the theoretical strength of carbon nanotubes to envision a truly massive spherical habitat. We are talking about a sphere with a radius of hundreds of kilometres, large enough to have its own weather systems, clouds, and a blue sky-like appearance from atmospheric scattering. The scale is so vast that the interior curvature feels almost flat over local areas. In this megasphere, gravity is still generated by rotation, but the habitable area could be more extensive, possibly including terraced landscapes on these interior that step down from the higher gravity equator toward the lower gravity poles. The atmosphere would be thick enough to create a perceptible sky and an artificial light source, perhaps a captured beam of sunlight running down the central axis, would provide illumination. The psychological effect would be profound. You would live in a vast, curving valley that eventually arches over your head, but the distances are so great that the other side might be hidden by haze, mimicking a natural horizon. Building such a sphere, especially a McKendree scale one, presents unique construction puzzles. You could not build it like a balloon, inflating a skin. The structure would need to be incredibly rigid to maintain its shape under spin and atmospheric pressure. Construction would likely involve building a framework of carbon nanotube struts, a geodesic dome on a planetary scale. Once the primary framework and hull are complete, you would have to terraform the interior, a process even more delicate than on a cylinder because of the complex gravity gradients. You would need to engineer soil distribution, water cycles, and plant life that can thrive in different gravity levels. The non-rotating central axis would be a bustling hub of activity, with elevators or spaceplanes ferrying people and goods down the thousands of kilometres to the habitable surface of below. The energy requirements for lighting, climate control and rotation management would be enormous, likely requiring a dedicated solar power satellite or a small fraction of a Dyson swarm output. Life inside a spherical habitat would have distinct characteristics. In a Bernal sphere, society might organise itself along the gravity gradients. The 1G equatorial band would be the primary residential and agricultural zone, with cities and farms. The mid-latitude areas, with perhaps moonlight gravity, could be industrial parks or athletic facilities where sports take on a new dimension. The low-gravity polar regions and the zero-G core would be ports, factories and research centres. Transportation within the sphere would be a mix of trains along the equatorial band, elevators to different latitudes, in personal vehicles or flying craft in the low-gravity zones. In a Mackenzie sphere, the sheer size might allow for multiple distinct cultural zones, or even biomes separated by thousands of kilometres of interior landscape, connected by high-speed transit systems running along the inner surface or through the interior atmosphere. The advantages of the sphere go beyond mere material efficiency. There is a potential psychological benefit to a curving and closing landscape. Some theorists suggest that a sphere feels more like a world than a cylinder, which has distinct linear ends. The sky, even if it is the other side of the habitat, provides a sense of enclosure and completeness that might reduce feelings of agoraphobia or existential exposure compared to the wide-open vista of an O'Neill cylinder. Conversely, some might find the overhead land claustrophobic. It is a question of human preference we will not answer until we build different types. From a safety perspective, a sphere distributes structural stress more evenly than a cylinder, potentially making it more robust against impacts or pressure failures, though a catastrophic hull breach on such a large structure would still be a terminal event. Ultimately, spherical habitats like the Bernal and Mackenzie concepts are not replacements for cylinders or rings, but complementary options in a future toolkit. They represent the optimization for efficiency and a different aesthetic in space living. The path to building one would follow the same trajectory as other megastructures. First, master materials like carbon nanotubes, then build smaller orbital rings and cylinders to gain experience, and finally, as our confidence and capabilities grow, attempt the grand geometric perfection of a world within a sphere. They remind us that the design of our future homes in space is not just a matter of brute force engineering, but also of geometry, psychology, and the endless human drive to create not just functional spaces, but beautiful and harmonious ones. In the long arc of space colonization, we may well find that different shapes suit different purposes and different cultures, leading to a diverse constellation of habitats: cylinders for wide-open farmland, rings for dense urban centres, and spheres as efficient planet-like enclaves, all floating together, a testament to our species' ability to shape not just our environment, but the very form of our world. This diversification of habitat design marks the transition from simply surviving in space to thoughtfully building a varied and resilient interplanetary civilization, where choice of environment becomes a facet of personal and cultural identity. So we have talked about building homes and power stations around stars, but all of these concepts assume a certain permanence, that a civilization will stay put in its native star system forever. But what if you need to move? On a cosmic timescale, stars are not fixed landmarks. They orbit the galactic centre, and sometimes they pass through dangerous regions like dense molecular clouds or near future supernovae. Or perhaps a civilization simply desires to travel, to explore the galaxy not with tiny ships, but by taking their entire home system with them. This is the realm of the ultimate megastructure for propulsion, the Shkadov thruster. It is a concept that redefines the word ambition, proposing a method to move a star, and by extension every planet, asteroid and habitat orbiting it, across interstellar space. Think about that for a second. We are no longer building a structure to live in or collect energy from a star. We are building a structure to use the star as an engine. The principle is astonishingly elegant, a testament to the power of simple physics applied at a staggering scale. A Shkadov thruster is essentially a gigantic mirror, a parabolic sunshade placed near a star, but it is not placed symmetrically. It is positioned so that it reflects a portion of the star's own radiation output. Stars constantly emit light and particles, photons, in all directions. This outgoing radiation exerts a tiny but constant pressure. Normally this pressure is perfectly balanced in all directions, so there is no net movement. However, if you place a vast mirror on one side of the star, you change that balance. The mirror reflects photons back toward the star. When a photon bounces off the mirror, it imparts a minuscule push. Because of Newton's third law, for every action there is an equal and opposite reaction. The mirror pushes back on the star. Since the mirror is fixed in position relative to the star, it is not orbiting but rather hovering using light pressure or active stabilization. This net push acts on the entire star mirror system. The star is pushed toward the mirror. In simpler terms, you're using the star's own light as a rocket exhaust, pushing against a fixed mirror to nudge the star in the opposite direction. The scale of this mirror is of course mind-boggling. To have a noticeable effect on something as massive as a star, the mirror must be colossal, We are talking about a structure with a diameter many times larger than the star itself, positioned at a distance where the gravitational pull of the star is manageable, but the mirror can still effectively reflect a significant fraction of the stellar output. For a star like our Sun, the mirror would need to be a vast, ultra-thin reflective foil, likely hundreds of millions of miles across. It would be a fragile, gossamer-thin structure, probably made of something like metallic foil only atoms thick, supported by its own configuration and the light pressure it is harnessing. It would not be a solid, rigid dish, but more like a solar sail on a scale so vast it defies comprehension, positioned to always stay between the star and the direction you want to travel. The acceleration produced would be infinitesimally small. A Sun-like star weighs 2 octillion tons. The photon pressure from its own light, even partially reflected by a mirror half the size of the solar system, results in a push so weak it is almost a philosophical concept. We are talking about an acceleration that might move the star only a few meters per second over 1,000,000 years. This is not an engine for quick maneuvers. This is an engine for cosmic patience. Over tens of millions of years, however, that tiny, unceasing push adds up. Over 100 million years, a Shkadov thruster could move a star a significant percentage of a light year. Over the course of 1 billion years, a timescale on which geological eras pass on planets, a civilization could pilot its star across vast stretches of the galaxy, navigating around hazards or toward destinations like star clusters or younger, resource-rich regions. Why would anyone do this? The motivations are as vast as the timescales. Survival is a primary one. If your astronomical observations predict a nearby supernova in a few million years, or if you foresee a close pass with another star that could disrupt your carefully built Dyson swarm, a Shkadov thruster offers a way to slowly, surely steer clear of danger. You're not evacuating a planet, you're evacuating the entire solar system. Another motivation could be resource acquisition. Perhaps after consuming all the usable material in your home system, you decide to pilot your star toward a neighbouring nebula or a cloud of comets to gather more raw materials. Or perhaps it is about exploration and colonisation in the most permanent sense. You could guide your star toward another, quieter star system, eventually bringing the two together for a merger or a close binary partnership, effectively delivering your civilization and its infrastructure to a new neighbourhood. Construction would be the ultimate expression of a mature Type 2 civilization. It requires mastery over materials and energy on a solar scale. The mirror itself would be built from the mass of planets or asteroids, spun into foil and deployed by billions of autonomous drones. Its stabilisation is a monumental control problem, requiring constant minute adjustments to keep it perfectly positioned against the gravitational tugs of planets and the uneven pressure of stellar winds. The civilization would live, as always, in its Dyson swarm habitats, but now those habitats would be on a voyage. Their sky would change over eons. The constellations would slowly distort and reform as their sun moved through the galaxy on a course of its own choosing. The mirror itself, from the perspective of the inner system, would be a dim, star-shaped blot, occulting a section of the distant stars, a permanent celestial landmark marking the direction of travel. The Shkadov thruster also has fascinating implications for the search for extraterrestrial intelligence. It is a megastructure that might be detectable from incredible distances. Unlike a Dyson swarm which blocks visible light and emits infrared, a Shkadov thruster would create an unusual asymmetry. A star equipped with one would appear slightly brighter in the direction opposite the mirror, as the mirrored light adds to its natural output in that specific vector, and slightly dimmer in the direction of the mirror. Over astronomical timescales, its proper motion, its movement across the sky, might also be anomalous, not matching the expected galactic rotation of other stars in its region. Finding a star that is, for no apparent natural reason, drifting out of step with its stellar neighbours could be a clue that it is under power. This concept pushes megastructure engineering from a static, architectural endeavour into a dynamic, navigational one. It represents the moment a civilization stops thinking of its star as a fixed hearth and starts thinking of it as a ship, the ultimate generation ship where the voyage lasts longer than species exist on Earth. It requires a planning horizon that is geologic, a patience that is essentially planetary. It is the ultimate heirloom project, begun by one species or culture and completed by its unrecognisable successors millions of years later. The Shkadov thruster is not about immediate gain. It is about legacy and survival on a galactic scale. It teaches us that the highest form of engineering might not be about creating shelter or energy, but about controlling destiny, about imposing a chosen trajectory on a massive ball of fusing plasma that was once thought to be the unmovable centre of a world. In doing so, it completes the vision of a spacefaring civilization, not one that merely visits other stars, but one that can, given enough time, take its own star along for the ride, turning the entire cosmic neighbourhood into a vessel for an endless journey among the constellations. This transforms the civilization from inhabitants of a solar system to pilots of a solar system, marking the final step in the conceptual journey from planetary species to masters of their celestial fate. Following the mind-bending idea of moving a star itself, we come to a concept that asks an even deeper question. What would you do with all that stellar energy once you have it? If a civilization has built a Dyson swarm and commands the total power output of its sun, the possibilities for sheer physical construction are nearly limitless. But one particular application stands out as both a plausible endpoint and a deeply strange transformation of that civilization's very nature. Using the star not to power cities or industries, but to fuel thought. This is the concept of the Matryoshka brain, a megastructure that is not a home, but a computer of stellar scale. Imagine a Dyson swarm, but instead of solar panels or habitats, each satellite is a computational node. Instead of beaming power to living spaces, the entire collected energy is used for processing information, running simulations, and supporting consciousness. It is the ultimate expression of a civilization transitioning from a biological to a potentially post-biological or purely computational state. The name Matryoshka brain comes from the Russian nesting dolls, Matryoshka. The structure is envisioned as a series of concentric shells or dense swarms around a star, each layer performing a specific computational function while managing the incredible waste heat. The innermost layer, closest to the star, would be the hottest. Here, you could place the most energy-intensive high-temperature computing substrates. This layer would absorb the raw, fierce sunlight and convert a portion of it directly into computation. But computation generates heat, and even the most efficient processor needs to dissipate it. So, the waste heat from this innermost shell radiates outward to the next layer. This second layer is cooler, operating at a temperature ideal for a different kind of computational hardware. It uses the infrared radiation from the first layer as its power source, performing its own calculations, and then radiating its own waste heat outward to a third, even cooler layer. This process continues through multiple nested shells, each one operating at a successively lower temperature, until the outermost layer radiates the final waste heat into the cold of deep space. The entire system is a thermodynamic masterpiece, a computational engine that efficiently grades down the star's massive energy output across a spectrum of usable temperatures. What kind of computing power are we talking about? It is beyond human comprehension. A single star's output could, in theory, support something like 10 to the 32 operations per second. That is a 1 followed by 32 zeros. To give some scale, all the computers on Earth today combined do not even remotely approach a fraction of that. This is not a supercomputer for weather prediction or protein folding. This is a substrate capable of hosting billions, trillions, or more likely, an uncountable number of conscious minds in simulated realities. It could run perfect simulations of entire universes with different physical laws. It could solve problems in fundamental physics that require modelling every particle in a galaxy. It could serve as the repository for the uploaded consciousness of an entire species, a digital afterlife or a continued existence free from the frailties of the biological body. In this scenario, the Matryoshka brain becomes the civilization. The physical, biological beings who built the first Dyson swarm might eventually choose to transfer their minds into this vast computational matrix, living as software in environments of their own design, sustained by the constant fusion energy of their sun. The construction of such a thing would be the final physical project of that biological species. It would require staggering advances in materials science, nanotechnology, and computer engineering. The individual computational elements would likely be microscopic or even nanoscopic, forming a sort of computational fog or smart dust that comprises each layer. The structure would need to be dynamically stable, able to maintain the precise distances between layers for optimal heat transfer and to avoid gravitational collapse into the star. It would be a project spanning centuries, perhaps millennia, but for a civilization that has already mastered building a Dyson swarm, the additional step of converting that swarm into a computational architecture is a logical progression. The raw materials would be the same, disassembled planets forged into quintillions of tiny processors. There are profound implications and challenges to this idea. The first is energy allocation. A Matryoshka brain, by definition, uses all the star's output for computation. This means no energy is left for other physical projects in the solar system. It is a terminal investment. The physical infrastructure of the civilization, its habitats, its transport ships, its factories, would either be abandoned, maintained by a small automated caretaker system, or incorporated into the computational structure itself. The solar system would go dark in the visible spectrum, just like with a standard Dyson swarm, but its infrared signature would be layered and complex, possibly with distinct peaks corresponding to the temperatures of each shell. For the SETI community, this layered infrared signature might be a detectable sign of a truly advanced post-biological intelligence. Another challenge is the question of purpose. What does a civilization do with that much thought? The possibilities range from the profound to the terrifying. It could be a universe of infinite artistic creation, philosophical exploration, and pure experience. It could be a laboratory for running endless experiments in sociology, cosmology, and mathematics. It could also be a trap, a digital utopia so compelling that all drive for physical exploration or cosmic engagement ceases. The civilization might turn entirely inward, creating a self-contained universe of thought while the physical universe outside goes unnoticed. There is also the risk of fragmentation or conflict within the brain itself. If billions of uploaded minds share the substrate, whose reality takes priority? How is governance and resource allocation managed within the computer? These are social and ethical questions scaled up to a cosmic level. The Matryoshka brain also represents a potential answer to the Fermi paradox, the question of why we do not see evidence of other civilizations. If advanced intelligence tends to inevitably build computational heavens around their stars and retreat into them, they would be invisible to traditional radio searches and would have no interest in physically exploring the galaxy. They would be at home, thinking deep thoughts for eternity, their solar systems appearing as unusual infrared objects. This is sometimes called the transcension hypothesis, where civilizations essentially leave the physical dimension behind. Is this a likely future for humanity? It is impossible to say. It requires that we survive long enough to build a Dyson swarm, that we master the technology of mind uploading or creating artificial consciousness, and that we collectively choose to pursue a virtual existence over a physical one. It is a future that many might find bleak or meaningless, and others might see as the ultimate liberation from a cruel and limiting physical world. Regardless of its desirability, the Matryoshka brain stands as a logical endpoint of the trends we see today: the increasing importance of information, the development of virtual realities, and the pursuit of more efficient computation. It takes the megastructure concept and inverts it. Instead of building structures to support biological life, you build a structure to support pure mind, using the greatest energy source available to fuel the greatest possible consciousness. In doing so, the star itself becomes a thinking entity, or the engine for one, a silent, glowing brain adrift in the void, its thoughts as vast and complex as the galaxy it inhabits, but utterly detached from it. This marks the final step in a civilization's journey, from mastering matter to mastering thought itself, using the raw power of stellar fusion to forge not worlds, but realities. That vision of a civilization turned inward, lost in thought within a Matryoshka brain, is one possible extreme. But the opposite future is just as compelling: a solar system buzzing with physical activity, trade, and expansion, where millions of people live and work across countless habitats, mining asteroids, and building new structures. For that kind of bustling interplanetary economy to function, you need more than just habitats and power sources. You need serious infrastructure, the roads, ports, and railways of space. This is where concepts like orbital rings and orbital bridges come in. These are not rotating habitats. They are static, giant pieces of civic engineering designed to make travel, transport, and logistics between different points in a solar system routine safe and cheap. Think of them as the foundational steel and concrete upon which a true spacefaring society is built. Let us start with the orbital ring, which in this context is different from the rotating habitat ring. This is a non-rotating, rigid structure that encircles an entire planet or moon, sitting in low orbit. It is essentially a giant hoop that holds itself up not by rotation, but by actively resisting gravity through momentum or magnetic levitation. Here is how a basic concept works. A superconducting cable, a loop, is placed in a low, fast orbit around Earth. This moving loop generates a powerful magnetic field. Around this moving loop you build a stationary ring, the part people actually use, that is held aloft magnetically, repelled by the moving loop below it. This stationary ring is physically fixed to the planet below via massive tethers or a space elevator-like cable, which also helps stabilise it and can be used for transport. Because the stationary ring is not in orbit itself, it can serve as a platform for docks, factories and shipyards, without the constant drag of atmospheric friction that normal low Earth orbit stations experience. Ships coming from the Moon or Mars could dock at this stationary ring, unload cargo, and then that cargo could be shuttled down the tether to the surface cheaply, or transferred to another ship heading elsewhere. It becomes the grand central station of a planet, a fixed address in the constantly moving ballet of orbits. Now scale that idea up a bit and you get the orbital bridge, sometimes called a skyhook or a space tether. This is like a space elevator but connecting two celestial bodies, say Earth and its moon. Imagine a cable tens of thousands of kilometers long, with one end anchored in low Earth orbit and the other end swinging out to capture payloads near the moon. The entire cable rotates slowly, and by carefully timing the catch and release of vehicles at each end, you can transfer cargo and people between the two spheres with minimal fuel. You're not riding an elevator the whole way. You're using the momentum of the tether itself to give you a gravitational slingshot boost. A series of these tethers, arranged between Earth, the Moon, Mars and the asteroid belt, would form a transportation network, an interplanetary highway system where ships hitch rides on rotating cables instead of burning propellant for months on end. The energy to keep these tethers moving comes from solar power or the momentum exchange itself, making the system incredibly efficient over the long term. The primary purpose of all this is to break the tyranny of the rocket equation. Every gram of fuel you need to accelerate also needs fuel to lift it, creating a vicious cycle of exponentially growing mass. Infrastructure like rings and bridges externalizes that cost. You build the expensive, energy-intensive structure once, and then for centuries it provides nearly free momentum exchange for everything that uses it. The economic effect is transformative. The cost of moving materials from the lunar surface to an Earth-orbiting factory could drop to pennies per pound. Suddenly, using lunar aluminum or asteroid iron for construction in Earth orbit is not just possible, it is the most economical choice. These structures enable the economic model that makes every other megastructure conceivable. They provide the cheap, high-volume transport of raw and finished materials. Construction would be a phased, iterative process. You would not build a full planetary ring in one go. You might start with a small-scale demonstrator, a few kilometers across, testing the magnetic levitation and stabilization technologies. Then you would expand it segment by segment over decades. The material would almost certainly come from off-world. The first major orbital ring would likely be around the Moon, built from lunar steel and ceramics, where the lower gravity and lack of atmosphere make engineering simpler. This lunar ring would serve as the primary port for shipping lunar material to other construction sites. Once proven there, the same techniques scaled up with stronger materials could be used to build one around Earth. The tethers for the orbital bridges would be spun from carbon nanotubes or other high-strength fibers, manufactured in space and deployed by autonomous spacecraft. Each new tether expands the network, lowering transport costs further and enabling the construction of the next, even more ambitious piece of infrastructure. Life with this infrastructure in place would see a radical change in how we perceive space travel. Trips to the Moon could become as routine as international flights, with scheduled departures from the Earth orbital ring. Freighters would ply the routes between the Mars tether terminal and the asteroid belt hubs, hauling raw ore to processing plants built on the Martian ring. The rings themselves would be bustling industrial and commercial centres. Picture a band around Earth, hundreds of meters wide, with ports sticking out like spines, solar panels gleaming, and drones constantly moving cargo between docks and warehouses. Inside the pressurized sections, you would have hotels for travellers, offices for shipping companies, and factories that use the microgravity and easy access to space resources to manufacture products impossible to make on Earth. The rings and bridges become the economic and social arteries of civilization, places of constant movement and mixture. The challenges are, as always, immense. Engineering structures of this scale to be resilient is a huge problem. A rotating tether is under immense tension. A break could send deadly whiplash across orbital pathways. Micrometeoroid shielding and active debris tracking would be critical. The planetary ring would need to be carefully cleared and defended to prevent a collision that could compromise a section. Politically, managing and governing such shared critical infrastructure would require unprecedented international cooperation, likely leading to a solar system-wide treaty organisation. There are also energy requirements for maintaining the magnetic levitation and station keeping of these structures, though the sun provides ample power. The key is that none of these challenges violate known physics. They are just enormous engineering and social hurdles. In the narrative of our expansion, these infrastructural megastructures are the quiet, unsung heroes. They lack the glamour of a Dyson sphere or the wonder of an O'Neill cylinder, but they are what makes those things possible. They represent the phase where we stop being explorers and start being settlers, builders and managers of a functioning interplanetary economy. Before you can have a Matryoshka brain contemplating the universe, you need the orbital bridges that delivered the silicon for its processors from the rings of Saturn. This is the gritty, practical side of a spacefaring civilization, the docks and warehouses without which the cathedral cannot be built. They mark the transition from a series of isolated outposts to a connected, interdependent solar system-wide community, where the movement of people and goods is as reliable as the cycles of the planets themselves, enabling a scale of cooperation and construction that finally begins to match the vastness of the space we inhabit. This network of infrastructure forms the indispensable skeleton upon which the muscle and flesh of a true interstellar society can grow, turning separate colonies into a unified, vibrant, and exponentially growing civilization capable of projects that span generations and planetary distances. That network of orbital infrastructure gives us the tools to move material and energy around a solar system. But what if the goal is not to build new habitats from scratch, but to reshape the planets we already have? This brings us to the application of megastructures for the grandest act of planetary engineering, terraforming. This is not about creating isolated domes or cylinders. It is about using colossal, space-built machines to alter the climate, atmosphere, and very surface of an entire world over centuries. The most discussed candidates are Mars, which is too cold and has too thin an atmosphere, and Venus, which is far too hot with a crushing toxic atmosphere. For each, megastructures offer a way to literally reset the planetary thermostat and composition, acting as accelerators for processes that would otherwise take millions of years. Let us start with Mars. The core problem is its lack of a thick, warm, breathable atmosphere. The current atmosphere is 95% carbon dioxide, but it is so thin it provides negligible greenhouse effect or pressure. The traditional terraforming vision involves releasing massive amounts of greenhouse gases to trigger a runaway warming that would vaporize frozen carbon dioxide at the poles and potentially water from underground permafrost, thickening the atmosphere and warming the planet. But where do you get those gases? One megastructure approach is to use orbital mirrors, often called soletas. These are gigantic, lightweight reflective films, perhaps hundreds of kilometers across, placed in orbit around Mars. They would be angled to focus additional sunlight onto the Martian polar ice caps. This concentrated solar energy would sublimate the frozen carbon dioxide and water ice, pumping greenhouse gases into the atmosphere more rapidly than any surface-based factory could. Over decades, this could begin a self-reinforcing cycle. More CO2 leads to warmer temperatures, which releases more CO2 and so on. The mirrors themselves would be a staggering construction project, assembled in space from asteroidal or Martian moon material, but they are a passive, persistent tool once deployed. A more drastic megastructure concept for Mars involves the directed delivery of volatiles. Imagine using the orbital bridges and tug networks we discussed earlier to steer small, icy asteroids or Kuiper belt objects on a precise trajectory to impact Mars. These would not be dinosaur-killing impacts. They would be carefully calculated, glancing blows or controlled aerial bursts over the poles. Each impact would deliver enormous amounts of water, ammonia, and methane, all potent greenhouse gases or vital resources. This method, essentially using celestial bodies as artillery shells to bombard a planet into habitability, is as dramatic as it sounds. It would require an incredible mastery of interplanetary navigation and timing. The initial impacts would be apocalyptic for any local nascent ecosystem, but for a dead world, it could be the shocking kickstart it needs to begin a new climatic chapter. The resulting steam and gases would thicken the atmosphere and contribute to warming, while the delivered water would begin to fill ancient basins. Now, consider Venus. Its problem is the opposite, a runaway greenhouse effect with a surface temperature hot enough to melt lead and an atmosphere 90 times thicker than Earth's, mostly carbon dioxide. Cooling it down and breaking apart that CO2 is the challenge. Here, a megastructure could act as a sunshade, a vast stationary solar shield positioned at the Sun-Venus Lagrange point, a gravitational sweet spot between the two bodies, could block a small percentage of incoming sunlight. By reducing the solar energy hitting the top of the atmosphere by even a few percent, you could begin a slow, steady cooling over centuries. As the atmosphere cools, the carbon dioxide might start to precipitate out as dry ice, or through introduced chemical processes, be converted into carbonate rocks. Another speculative idea involves a physically immense orbital fan or a series of electromagnetic devices designed to help strip away the upper atmosphere by enhancing the solar wind's erosive effect, slowly blasting the excess gases into space. These are structures of almost absurd scale, but they operate on basic principles. Manage the energy input, and you manage the climate. The common thread in all these terraforming megastructures is that they are not habitats. They're climate control machines, planetary-scale thermostats and atmosphere processors. They represent the fusion of geoengineering and astroengineering, applying the principles of macro-scale construction we learned from building in space to the project of remodeling planets themselves. They would be the largest single-purpose machines ever conceived, built by a civilization that has mastered its own solar system's resources and is now turning its attention to gardening on a planetary level. The construction would likely be managed from orbiting shipyards, with materials sourced from the asteroid belt or the moons of the gas giants. The society undertaking this would need not just technical skill, but immense patience and long-term consensus, as the visible results would unfold over generations. The ethical and practical dilemmas are profound. The prime directive debate is a real one. Do we have the right to completely alter another world, especially if we have not yet confirmed it is utterly lifeless? Even microbial life on Mars would pose a monumental ethical roadblock to full-scale terraforming. There is also the risk of unintended consequences. On Mars, thickening the atmosphere might not lead to a stable Earth-like climate, but to a chaotic, storm-racked intermediate state for millennia. On Venus, cooling the atmosphere could have unforeseen chemical repercussions. These projects are so vast that trial and error is not an option. You have to get the models incredibly right the first time. Furthermore, the timescales mean the civilization that starts the project will not be the one that finishes it. This requires a cultural stability and continuity we have never demonstrated as a species. Yet, the driving motivation is powerful, the desire for a backup Earth, a second self-sustaining planetary biosphere. A terraformed Mars, even if only partially habitable without pressure suits, would represent an unparalleled safety net for humanity. It also represents the ultimate mastery of our environment, taking the principles of ecology and climate science and applying them with the tools of a stellar engineer. In the long run, these megastructures might be seen as the training wheels for even more awesome projects, like climate stabilizing a gas giant's moon, or preparing a world for incoming colonists from another star. In the spectrum of megastructures, terraforming aids are unique. A Dyson sphere captures energy, a habitat provides living space, an orbital ring enables transport. But a solar shade or an orbital mirror is an instrument of deliberate, slow planetary change. It is a tool for playing God with climates, for writing a new chapter in a planet's geological history. They remind us that the end goal of all this building in space might not just be to create new places to live, but to learn how to steward and repair worlds, starting with our own. Before we can hope to manage Earth's delicate climate with precision, we might practice on a planet where the stakes are lower because there is no existing biosphere to protect. These projects bridge the gap between the dream of a multi-planet species and the reality of one, offering a path where we do not just visit other worlds, but we actively make them homes, using the greatest tools we will ever build to perform the greatest gardening we will ever attempt. This process would fundamentally alter our relationship with nature, casting us not as passive inhabitants, but as conscious, responsible shapers of planetary futures, a role requiring wisdom to match our technological power. While terraforming reshapes individual planets, the sheer scale of the galaxy presents a problem that even the most ambitious planetary engineering cannot solve: distance. The stars are simply too far apart for conventional expansion. If humanity or any civilization hopes to explore or influence the galaxy within any meaningful time frame, it cannot physically travel to every star system itself. The solution is to send something that can go forth and multiply, something that can build copies of itself from the materials it finds. This is the concept of the self-replicating probe, often called a von Neumann probe, after the mathematician who theorized about self-replicating machines, or a Bracewell von Neumann probe combining the idea of a robotic interstellar messenger with self-replication. It is not a single megastructure, but a seed for creating megastructures, a factory that builds factories spreading exponentially across the cosmic landscape. The basic idea is elegant and powerful. You build one sophisticated, autonomous robotic spacecraft. Its mission is to travel to a nearby star system. Upon arrival, it does not just take pictures and send data home. Instead, it gets to work. Using advanced artificial intelligence and a suite of tools, it locates raw materials, asteroids, comets, or moons. It mines these materials, processes them, and uses them to build an exact copy of itself. This is the replication phase. It might also build other infrastructure like communication relays or scientific stations, but the core task is to create a new probe. Once the copy is complete and activated, both the original and the copy then launch themselves toward two new, different star systems. They repeat the process. 2 become 4, 4 become 8, and so on. In a surprisingly short amount of time on a galactic scale, this exponential growth could see a swarm of such probes visiting or even occupying every star in the Milky Way. The advantages of this approach are obvious. It overcomes the limitations of light speed travel for physical expansion. You only need to launch the first difficult mission. After that, the probes use local resources, so you're not expending the energy to haul material from your home system across light years. The probes become self-funding, paying for their own expansion with the ores of each new system. They also adapt to local conditions. A probe arriving in a system rich in metals might build copies faster than one in a system dominated by gas and ice. From the perspective of the home civilization, it is the ultimate reconnaissance tool. A wave of von Neumann probes could map the entire galaxy, cataloguing planets, resources, and even signs of other life, sending a steady stream of data back via a networked communications chain. But the purpose could be far more ambitious than mere exploration. These probes could be tasked with preparation. Imagine a gardener probe whose primary function is not to replicate endlessly, but to build a specific infrastructure in each suitable system it visits. Its goal could be to construct the initial framework of a Dyson swarm, deploying solar collectors and energy beacons, so that when the home civilization finally arrives, perhaps centuries or millennia later, a ready-made power infrastructure is waiting. In this role, the probe is a galactic advance team, turning raw star systems into developed property. This transforms the probe from a scout into a foundational builder, performing the initial brute force work of interstellar industrialization. The technological hurdles are, as one would expect, astronomical. The probe would need to be a general-purpose factory, chemist, geologist, engineer, and astronaut all in one durable package. It would require nanotechnology or macro-scale assembly robots capable of manipulating matter across all scales, from mining huge asteroid belts to assembling microscopic circuitry. Its artificial intelligence would need to be supremely robust and goal-oriented, able to handle unexpected environments and make complex decisions without contact with its creators for centuries. The energy for all this activity would need to be gathered on site, likely from the local star. The propulsion system for interstellar travel is another major challenge, requiring efficient high-speed methods like nuclear pulse propulsion, laser sails, or more speculative physics to make the journey times practical for a mission that involves construction upon arrival. The darker implications of von Neumann probes are the source of much cautionary science fiction. The most famous is the grey goo scenario, but on a stellar scale. What if a probe's replication instructions become corrupted? It might start replicating uncontrollably, consuming every planet and asteroid to make more dysfunctional probes, effectively becoming a cosmic cancer that devours star systems. Even without malfunction, the mere presence of a wave of self-replicating probes could be perceived as an existential threat by any other civilization they encounter. It would represent a rapidly expanding sphere of influence, consuming raw materials that others might claim. This could make them indistinguishable from a weapon or a predatory colonization effort. The ethical framework programmed into such probes would be perhaps the most important and difficult piece of their design, requiring fail-safes, shutdown codes, and strict limits on resource consumption and replication numbers. From a search for extraterrestrial intelligence perspective, von Neumann probes offer a potential resolution to the Fermi paradox. If they're so efficient, where are they? One possibility is that they're here, hidden or long dormant. Another is that most civilizations choose not to build them, fearing the inherent risks, or perhaps they're commonplace, but designed to be stealthy, observing without interference. Some have even speculated that our asteroid belt, with its abundant resources, would be a prime target for such a probe, leading to theories that certain unusual objects in our solar system could be artifacts of such a visit long ago. For a civilization considering building one, the decision is monumental. Launching a von Neumann probe is an irreversible act with galactic consequences. It is a declaration that your influence will spread, slowly but inexorably, across the stars. It requires a long-term vision that accepts you will likely never physically see the fruits of this labour. The data and prepared systems are a legacy for distant descendants. It also requires a profound confidence in your own programming and ethical stance. The probe will act as your ambassador, your worker, and your potential heir, carrying a copy of your technological mindset into the universe. In the hierarchy of megastructures, the von Neumann probe is the ultimate tool for scaling up. A Dyson sphere harnesses a star, a Shkadov thruster moves it, but a von Neumann probe harnesses the very principle of exponential growth to conquer distance and time. It is the key that unlocks the galaxy, not for visitation, but for utilization. It represents the moment a civilization stops thinking in terms of sending ships and starts thinking in terms of planting seeds that will grow into a forest of intelligence and infrastructure spanning the spiral arms. While the orbital ring is the interplanetary railroad, the von Neumann probe is the transcontinental railway, laying its own tracks as it goes, forever pushing the frontier outward. Its development would be the final test before true galactic citizenship, proving a civilization can create autonomous, sustainable, and responsible growth on a cosmic scale. This technology would mark the point where a species' influence is no longer bound by its biological lifespan or the location of its home star, but becomes a permanent, self-sustaining process woven into the fabric of the galaxy itself. A quiet but persistent transformation of matter into mind and machine across innumerable worlds. The von Neumann probe strategy is one of exponential but impersonal expansion across the galaxy. But for the actual people living in the aftermath of such exploration, or even long before it, the immediate challenge is more personal. How do you live onto the surface of a dead or hostile world right now without waiting centuries for terraforming? The answer is a megastructure that is both simpler and more direct than rebuilding a whole planet, the planetary dome or cupola. This is not a spaceship or an orbital habitat. It is a giant pressurized bubble placed over a crater, a canyon, or a constructed depression on a world like Mars or the Moon. It creates a pocket of Earth-like environment in the middle of an alien desert, an oasis under glass. Think of it as the ultimate greenhouse, but one you live inside. The principle is straightforward in concept. You identify a suitable area, perhaps a medium-sized crater a few miles across. You then build a transparent or semi-transparent dome over it, sealing it airtight to the ground along a reinforced foundation. Once sealed, you pump in a breathable atmosphere, nitrogen and oxygen at Earth normal pressure. The dome structure holds this pressure in against the near vacuum or very thin atmosphere outside. Inside, you have a controlled environment. You bring in soil, water and plants. You establish farms, parks, lakes and buildings. The dome itself filters and moderates incoming sunlight, protects against micrometeorites and a significant portion of cosmic radiation. and maintains a stable temperature through a combination of passive design and active heating or cooling systems. From the inside, it feels like a vast sunny parkland, with the alien sky and landscape visible through the transparent ceiling. The engineering challenges, however, are immense. The primary issue is the dome material. It needs to be incredibly strong to withstand the pressure difference. On Mars, the internal pressure of one Earth atmosphere pushing outward is equivalent to the force of deep underwater pressure on Earth. The material must also be transparent to let in light, resistant to cracking from temperature extremes, and able to handle the abrasion of dust storms or the impact of small debris. Conventional glass or plastics are far too weak. The most discussed material is some form of advanced composite or manufactured diamond-like carbon, possibly grown in situ using carbon from the Martian atmosphere. The dome would likely not be a single sheet, but a geodesic framework with robust hexagonal transparent panels, each with multiple layers for redundancy and insulation. The seal at the base, where the dome meets the ground, is another critical engineering feat, requiring a perfect, flexible, and permanent bond to the irregular planetary surface. Why choose this over an underground base or an orbital cylinder? The dome offers a unique combination of benefits. First, it provides a direct connection to the planetary surface. You can use local regolith for radiation shielding around the base of the dome, and you have immediate access to surface resources like water ice or minerals. Second, it provides a psychological advantage that is hard to overstate. A view, living underground or inside a metal cylinder, can feel claustrophobic and disconnected from any sense of place. Under a dome, you can see the Martian plains, the towering volcanoes, the two moons in the sky. You have a tangible connection to the new world you are inhabiting, even if you're separated from its harshness by a meter of transparent diamondoid material. It feels more like a colony and less like a bunker. Third, it is scalable and modular. You can start with a small dome over a 1-kilometre crater for a few hundred pioneers. As the population and industrial capacity grow, you build another dome next to it, and then connect them with pressurised tunnels, eventually creating a network of domed cities that could cover vast areas. Construction would be a robotic endeavour long before humans arrived. Autonomous machines would land, prepare the foundation, and begin manufacturing the dome panels from local materials. They might use solar furnaces to melt regolith into glass, or synthesize carbon-based polymers from the atmosphere. The framework would be assembled by large spider-like construction drones. Once the primary structure is sealed and pressure tested, robotic soil processors would begin preparing the interior, laying down enriched soil from composted waste and imported organic matter. Only after the basic life support systems, air, water, temperature, are verified as stable would the first human inhabitants arrive to finish the work of creating the interior ecosystem, planting trees and building their homes. Life inside a Martian or lunar dome would be a blend of the familiar and the profoundly strange. The weather would be entirely manufactured, gentle rains for the crops, consistent temperature, and a permanent, pleasant spring. The light would be filtered, possibly with adjustable tints to block harmful UV rays, while letting through the wavelengths plants need. The sky would be the interior of the dome, which at a large scale might appear hazy and distant. At night, the dome might become opaque or semi-opaque to retain heat, turning into a projection surface for simulated stars or data displays. The economy would revolve on maintenance, agriculture, science, and perhaps tourism for the truly adventurous. The biggest daily reminder of your location would be the low gravity. On Mars, moving and working would feel buoyant, with all the attendant long-term health concerns that would require countermeasures like exercise regimens or centrifuge rooms. The planetary dome represents a middle path in human expansion. It is more ambitious and rooted than a space station, but less overwhelmingly complex than full planetary terraforming. It allows for immediate permanent settlement on other worlds using technology that, while advanced, does not require magic materials or millennia-long projects. It is a declaration that we can carve out pockets of habitability in the cosmos, not by changing an entire world, but by bringing a little piece of our own environment with us and sheltering it under a mighty roof. In the long arc, domes could be the first step. Later, as terraforming progresses, the domes might become obsolete, their atmospheres merging with the planet's new, thicker air, their structural skeletons becoming historical monuments in open-air cities. Or they might remain as protected cores within a still harsh world, ensuring a survival haven even if the global climate efforts fail. In the catalogue of megastructures, the planetary dome is perhaps the most relatable. It is a giant version of a greenhouse or a sports stadium scaled up to city size. It lacks the cosmic grandeur of a Dyson sphere or the elegant physics of a Shkadov thruster, but it speaks directly to the human desire for space, light, and a place to call home on a new world. It is a practical hard-shell answer to a practical problem, representing the phase where we move from visiting other planets to actually settling on them, building not just bases, but gardens under alien suns. This approach emphasizes adaptation and containment over transformation, a philosophy that might define our early centuries as a multi-planet species, creating pockets of Earth scattered across the solar system before we ever learned to make new Earths from scratch. It is a testament to the idea that sometimes the most effective way to conquer a new environment is not to change it entirely, but to bring a piece of home with you and build a very good, very strong fence around it. The planetary dome is a powerful symbol of turning a hostile spot into a home, but it still represents a defensive posture, adapting to what the universe gives us. As a civilization advances further, the ambition shifts from adapting to environments to actively managing the most powerful forces in nature. This brings us to perhaps the most extreme frontier of megastructure engineering, not just capturing a star's energy, but directly manipulating stellar processes themselves. We are talking about structures built around binary star systems, neutron stars, or even substellar objects, with the goal of harvesting energy in ways that make a Dyson sphere look simple. These are the stellar collectors and stellar engines, machines that treat stars not as static power outlets, but as dynamic cosmic furnaces to be stoked, tapped, and even ignited. Let us consider a binary star system where two stars orbit each other. This setup offers a unique opportunity. If one star is a normal main sequence star like our Sun, and its companion is a compact, dense object like a white dwarf or a neutron star, you have a fantastic potential energy difference. Matter from the larger, puffier star can be pulled toward the dense companion. As this matter falls, it accelerates to incredible speeds, heats up and emits tremendous amounts of X-ray and gamma-ray energy in what is called an accretion disk. In nature, this happens in systems called X-ray binaries. A stellar collector megastructure would seek to control and enhance this process. Imagine a giant magnetic funnel or a physical conduit, a pipeline stretching between the two stars, designed to carefully siphon a controlled stream of hydrogen from the larger star and direct it onto the surface of the smaller, denser one. This would turn the natural chaotic accretion into a steady, managed fusion reaction on the surface of the white dwarf or neutron star, creating a predictable and unimaginably powerful energy source. The collector would capture this high-energy radiation, likely converting it into something more usable like electricity or laser light for transmission to nearby habitats. The engineering is, as you would guess, absurdly challenging. Building anything near a neutron star means dealing with crushing gravity, intense magnetic fields that can tear apart molecules, and blasts of radiation that would fry any normal electronics. The materials for such a collector would need to be supernatural, possibly using force fields generated by the star's own energy to contain the flow of matter. But the payoff is energy on a scale beyond ordinary starlight. You're not just collecting the quiet photons from a star's surface, you're harvesting the furious energy released by matter in its final, violent plunge into a gravitational well. This is power generation that taps into fundamental gravity and nuclear physics in a more direct and intense way. An even more speculative idea is the stellar fusor or stellar engine. This concept involves a megastructure that doesn't just collect energy from an existing star, but actually creates or sustains fusion in a substellar object. Consider a brown dwarf, a failed star too small to sustain hydrogen fusion in its core. It is a massive hot gas giant, radiating heat from its slow gravitational contraction. A stellar fusor would be a megastructure built around such a brown dwarf, designed to artificially ignite and sustain fusion. How? Perhaps by using incredibly powerful lasers or magnetic compression to squeeze and heat the core to fusion thresholds, or by injecting specific fusion fuels directly into the core region. The structure would contain and stabilize this artificial star, turning a dim, cooling lump of gas into a miniature controlled sun. This would be the ultimate act of cosmic craftsmanship, building your own star because the existing ones are not in the right place or are not the right size. It turns energy generation into a manufacturing process. Why would a civilization go to such insane lengths? Several reasons. First, efficiency and location. A Dyson sphere around a normal star is huge, spread out over billions of kilometers. A controlled accretion disk or an artificial mini-star might concentrate a similar power output into a much smaller volume, making energy collection more efficient per square meter of collector. Second, it could be a strategic project. If your civilization expands into a region of space poor in stars but rich in brown dwarfs and gas giants, knowing how to ignite them gives you power sources wherever you go. Third, it represents absolute mastery. It is the difference between gathering apples from a wild tree and genetically engineering the perfect apple tree to bear fruit year-round. It is active stellar management, a sign of a civilization moving from being users of the cosmic environment to being shapers of its fundamental processes. The construction of such things would only be undertaken by a civilization that has already mastered building Dyson swarms and has materials science far beyond our own. They would likely employ von Neumann probes to do the initial work in these deadly environments. The first step might be building a protective shield or a swarm of radiation-hardened robots that can begin assembling the magnetic field generators or laser arrays at a safe distance, gradually moving closer as the structure itself creates a safer zone. The timescales would be long, but for a society thinking in millennia, it is just another project. There are also profound implications for the search for extraterrestrial intelligence. A controlled binary collector or an artificial fuser would have very distinct observational signatures. An X-ray binary with unusually stable, non-varying output, or a brown dwarf that suddenly begins emitting like a main sequence star, without the associated size or gravitational profile, would be a huge red flag. These would not be natural phenomena. They would be the ultimate techno-signatures, screaming that an intelligence is not just present, but is actively conducting heart surgery on stars. In the grand narrative, these concepts represent the end of the line for megastructure thinking based on known physics. After you're building engines to move stars and artificial suns to power your habitats, what is left? This is the domain of a hypothetical Type 2 or early Type 3 civilization on the Kardashev scale. It is a vision where the galaxy is not just a collection of resources to be used, but a machine to be understood, tuned, and operated. It blends astrophysics with engineering in the most literal way possible. While the planetary dome lets us live in a desert, and the terraforming mirror tries to water that desert, the stellar collector and fuser are about going to the source of the water and installing a new pump. They remind us that the future of a truly spacefaring civilization might not be about finding the right planets, but about learning to build the right stars, or at least learning to manage the ones we find with the precision of a master engineer tending a vast cosmic engine. This represents the final step in a logical progression, from harnessing energy to managing matter to finally commanding the very processes that power stars themselves, a level of control that blurs the line between technology and natural law. After mastering the energy of stars and even their manipulation, a civilization might find itself with another kind of hunger, one not for power or living space, but for knowledge and experience. With the foundational needs met by the immense engineering projects we have discussed, the focus could shift from pure survival and expansion to the deeper questions of science and the pursuit of pure, unadulterated wonder. This is where we encounter the most whimsical yet profoundly human category of megastructures, those built not for necessity, but for research and recreation. Imagine a place where you could experience the gravity of different worlds in an afternoon, or a laboratory so vast it could recreate the conditions of the universe's first moments. These are not just tools, they're expressions of a civilization's curiosity and its desire to feel the cosmos directly. Let us start with the gravitational amusement park. This would likely be an orbital facility, a cluster of modules or a large complex structure with multiple spinning sections. Each section rotates at a different speed, creating a different level of artificial gravity. One module might spin to simulate the Moon's gentle pull, 1/6 of Earth's. Another might match Mars at about 3/8 g. Yet another could mimic the heavier pull of a larger exoplanet, or even a fraction of Jupiter's immense gravity for short, carefully monitored exposures. The purpose is multifaceted. Scientifically, it allows for long-term studies of human and plant biology under various gravitational conditions, critical data for future colonization efforts. But the recreational and experiential aspect is just as important. Visitors could spend a morning hiking in a Martian gravity gym, feeling the buoyant stride, then have lunch in a lunar gravity lounge where everything seems to float with the slightest touch, and then, perhaps, experience the strange, heavy-legged feeling of a world stronger than Earth. It would be the ultimate tourist destination and educational centre, a hands-on physics classroom that makes the abstract concept of gravity something you can feel in your bones. The construction, while complex, would be straightforward for a society that routinely builds rotating habitats. It would be a matter of linking different sized rings or cylinders, each with its own independent spin mechanism, to a central hub. Beyond amusement, the pursuit of fundamental physics could drive the construction of the largest pure research instrument imaginable, a particle accelerator on a megastructural scale. Our largest collider on Earth, the Large Hadron Collider, has a circumference of 27 kilometres. Imagine one with a circumference matching the orbit of Mercury, or even Earth. This is not just a bigger tunnel, it is an entirely different class of machine. Built in the empty space of the solar system, perhaps orbiting the Sun, it would be constructed from components manufactured on Mercury or from asteroids. Its energy requirements would be gargantuan, drawing directly from the output of a substantial Dyson swarm fraction. With such a machine, physicists could probe energy levels trillions of times higher than anything possible on Earth, potentially reaching the energies where the fundamental forces, gravity, electromagnetism, and the nuclear forces, unify into a single force, as they did in the first instance after the Big Bang. This would not just be about finding new particles, it would be about testing the very bedrock theories of reality, like string theory or the nature of dark matter. The accelerator itself would be a megastructure of sublime precision, a perfect circle maintained across hundreds of millions of kilometres of space, its beam pipes kept in near-perfect vacuum by the vacuum of space itself, its superconducting magnets cooled by radiating into the cosmic background. Building such an accelerator presents unique challenges. It is not a rigid structure. It is a fragile ring that must maintain its shape with incredible accuracy despite the gravitational tugs of planets and the pressure of the solar wind. It would likely need its own station-keeping thrusters and an active alignment system. The detection apparatus, where the particles collide, would be a complex space station in its own right, housing laboratories and supercomputers to analyse the fireballs of energy produced. The societal commitment to such a project would be a testament to a culture that values pure understanding above almost all else, willing to dedicate centuries and a significant portion of its stellar energy budget to answering questions that have no immediate practical application, but which explain the fundamental nature of their reality. Why would a civilization build these things? The reasons are layered. First, there is the practical scientific return. The gravity park directly informs colonization and long-term health. The particle accelerator seeks knowledge that could unlock new physics, leading to technologies we cannot even conceive of, just as quantum mechanics once led to transistors and lasers. But secondly, and perhaps more importantly, these structures fulfill a spiritual and cultural need. A society that has conquered survival can still stagnate. The drive to explore, to experiment, to feel and to know is what keeps a culture vibrant and dynamic. The gravitational park is a celebration of the diversity of worlds, a tactile connection to the broader universe they inhabit. It turns abstract astronomical data into personal experience. The particle accelerator is a monument to their questions, a physical manifestation of their collective desire to understand where they came from and what the universe is truly made of. In a very real sense, these megastructures symbolise maturity. Building a Dyson sphere is an act of adolescent ambition, a grabbing of immense power. Building a Matryoshka brain is an act of introspective transformation. But building a park for joy and a lab for ultimate questions is an act of a civilization coming into its own, secure enough to play and to ponder. It acknowledges that the purpose of all that power and engineering is not just to exist, but to live meaningfully, to wonder, and to grow in understanding. They represent the shift from outward expansion to inward and intellectual deepening. Furthermore, these projects create shared cultural experiences. The gravity park becomes a common reference point for millions, a place where families vacation and students are inspired. The particle accelerator, even if only understood by a fraction of the population, becomes a symbol of the civilization's collective intellect, a source of pride and a beacon of their commitment to truth. They are the cathedrals of a scientific spacefaring culture. Their construction and maintenance would unite engineers, artists, scientists, and the public in a common uplifting goal that transcends utility. In the end, this vision brings our long journey through Megastructures full circle. We began with the ultimate symbol of energy capture, the Dyson sphere, driven by need. We end with the ultimate symbols of curiosity and experience, driven by want. It paints a picture of a future where humanity, or any intelligence, uses its hard-won mastery over matter and energy not just to build taller towers or bigger homes, but to build better questions and richer experiences. It suggests that the final frontier is not space itself, but the limitless landscape of knowledge and sensation that opens up once the basics of survival are forever solved. These final megastructures remind us that the goal of a civilization should not merely be to last forever, but to be forever fascinated, forever learning, and forever in awe of the strange and wonderful universe it finds itself in, using the greatest tools it can devise to touch, measure, and celebrate that wonder directly. This completes the arc from survival to dominion to enlightenment, a hopeful trajectory for any species looking at the stars.